When we analyze a physical structure, we intuitively grasp its scale. But in algebra, how do we measure the size or complexity of an expression? To quantify that scale, mathematicians isolate a strict structural property known as the degree. This metric provides the necessary bounds for higher-level operations. In the polynomial division algorithm, the divisor's degree determines exactly when the process must terminate. Understanding a polynomial requires isolating and quantifying its smallest atomic units first, before judging the complete system. Look at this expression, a multivariable polynomial, 3x cubed plus 4x squared y squared plus 10y plus 1. Because we have multiple variables, x and y, competing for attention across different terms, it is difficult to accurately gauge the expression's overall scale at a glance. To find the degree of this specific expression, we cannot evaluate it as a single block. Instead, we must deconstruct it using a rigid, bottom-up mathematical hierarchy. We start by pulling focus away from the whole equation and isolating its most complex single term, 4x squared y squared. The absolute base level of our hierarchy is the degree of a single, isolated variable within a term. The first rule is straightforward. A single variable's degree is exactly its exponent. Looking at our isolated variables, the x has a degree of 2, and the y variable also has a degree of 2. To determine the unified degree of the entire multivariable term, we move one step up the hierarchy. The second rule requires summing the degrees of all individual variables within that specific term. 2 plus 2 equals 4, so the total term degree for 4x squared y squared is 4. Now we zoom back out to view the complete 4-term expression. The first term, 3x cubed, has only one variable. Its term degree is simply 3.
In the third term, 10y, the unwritten exponent implies a 1, meaning its term degree is 1. The final term is the constant, 1. Unlike the previous terms, there is no visible variable here to provide an exponent. A constant value mathematically implies the presence of variables raised to the power of 0. Because any non-zero number to the power of 0 equals 1, the overall value of the term is unchanged, but now the exponents are visible. Since 0 plus 0 is 0, the degree of any non-zero constant is always exactly 0. This brings us to the final rule for evaluating the entire polynomial. The total degree of the polynomial is the largest term degree found in the expression. We compare our calculated term degrees, 3, 4, 1, and 0, and identify the maximum. Despite the mix of variables and terms, this entire expression is definitively classified as a polynomial of degree 4. By adding these exponents together, we mathematically collapse complex, multivariable terms into a single, highly quantifiable metric of scale. If a non-zero constant has a degree of 0, we have to consider the specific case of the number 0 itself. The number 0 can be mathematically expressed as 0 multiplied by x raised to any power, without ever changing its value. Because these exponents can increase infinitely, it is impossible to locate a maximum degree. This establishes a constraint on our calculations. A degree can only be defined by terms that possess non-zero coefficients. The zero polynomial is a vital mathematical edge case. Leaving its degree undefined strictly protects higher-level algorithms from logical collapse. With the mechanics of degree calculation established, we translate these numbers into formal vocabulary. This matrix is a strict hierarchy that names polynomials based on their maximum degree. At the base, degree 0 is always a constant, provided the constant is not 0. Moving up to degree 1, we have linear polynomials. This classification system applies strictly to multivariable polynomials as well. Consider the expression x plus y. This expression is linear because the maximum degree of any single term within it is 1. Variables do not increase the total degree unless they share a term. The remaining formal terms complete the standard nomenclature: quadratic for degree 2, cubic for 3, quartic for 4, and quintic for degree 5. Finding the degree is the essential first step in algebra. Calculating these exponents establishes the exact mathematical identity of the polynomial before you attempt to solve or graph it.